Hello everybody, welcome to the fourth lecture in this discussion on chemical kinetics. Just a brief recap, actually a very quick recap. You know what we did last class was we started looking at kinetic reaction profiles, right, and this was the reaction profile we were looking at. This was an example where the reactants were hypochlorite and bromide and the products were hypobromide and chloride. It is a very simple reaction. The stoichiometry is 1 for each reactant and each product, and then what we were saying was that if you look at the blue lines are belonging to those of the reactants. What are we plotting here? We are plotting concentration versus time, right, here time being in seconds, and because the blue lines correspond to the reactants, and since with the progress of the reaction the reactants are going to be decreasing, that means used up, the products are going to be formed. Hence, you see that the blue lines, the concentration, if you go along the blue line, the concentration is decreasing, okay, as a function of time. The reverse happens for the products. Why? Because for the products here these are being formed as the reactants are being used up, and hence the products according to the green line or along the green line they are increasing as a function of time. Then we started asking the question as to how fast is this happening, can we have a quantitative estimate of the same, right. So, how can we have that, or how did we write that last time? So, if you remember, the rate of reaction can be either expressed in terms of rate of disappearance of reactants, or it can be expressed as rate of appearance of products. So, you can either do it in terms of the reactants which are decreasing as a function of time, or you can do it in terms of products which are increasing as a function of time, right. Because it is the rate of disappearance, we also discussed this last time. So, for reactants, if you are expressing the rate of reaction in terms of the reactants, and in this case the reactants being hypochlorite and bromide, we can express them as, so this I will just cancel, what I meant was the rate of reaction. You can express them like this: the change of the reactant hypochlorite over a defined time interval with a negative sign, or the change of the concentration of bromide over a time interval with the change in sign. Then we also said that suppose my delta hypochlorite, which is this one, the delta hypochlorite corresponds to say C1 and C3, that means C3 minus C1, and the delta T, I am talking here delta T, the delta T corresponds to T3 minus T1. So, what you will see is, if I express it like this again, C3 minus C1, then T3 minus T1. Okay. The first one is a negative quantity, that means the numerator is a negative quantity, the denominator is a positive quantity, and we get a negative value out here. Because this is negative, the rate cannot be negative. So, you have a negative sign out here, this negative and this negative cancels out, and finally, you have a positive value for the rate of the reaction. Now, this is extremely important that you understand. For any reactant, this is always maintained. If you are expressing the rate of the reaction in terms of products, right. So, that means again, if I expressing the rate of reaction in terms of products, I can express them as this, delta T, right. And if you take the same intervals For example, suppose you take T1, T3 for hypobromite or chloride, then T3 minus T1 is obviously positive because time is increasing, and again if you consider this concentration and this concentration is higher than that. So, this is positive over positive, which gives you a positive quantity. So, in terms of products, it is always a positive quantity, right. Okay. So, now let us start with a reaction. So, let us consider a very general reaction, right, a very general reaction. Let us see how we can represent that. So, the general reaction goes like this, right. A, small a, which is the stoichiometric coefficient of this chemical species A, small b, the small b is the stoichiometric coefficient of the reactant B plus other reactants, giving you this reaction. So on. So, this is a very general representation of a reaction. So, what A and B, C and so on are the reactants, right. Then small a, small b, small c, these are the corresponding stoichiometric coefficients. Similarly, P, Q, and if I write R out there, these are products, and in the same way the small p, the small q, the small r, these are stoichiometric coefficients of the products. The point I am trying to make out here is this: let the stoichiometric coefficients be represented as something referred to as nu, okay, nu, spelled as Nu, nu. If the general symbol of the stoichiometric coefficient is given as nu, then what we can write is, and this is extremely important that we follow and we understand, that for reactants or reactant species, this nu is a negative quantity. For products, nu is a positive quantity. Okay. So, that means if you go back to this, equation, then if I am writing nu for A, so if I am writing nu for A, then it would be minus A. If I am writing nu for B, it would be minus B. On the other hand, if I am writing nu for P, it would be plus P. If I am writing nu for Q, it would be plus Q, and so on. So, that means as I have written it here, for reactants the stoichiometric coefficient is considered to be negative. For products, the stoichiometric coefficient is considered to be positive, right. Now, why did we do this exercise? You will soon realize. Let us go back to a very general reaction and let us take a shortened form of that reaction. So, let us write the reaction again. So, the reaction again can be written like this: A plus B, giving us the product P plus the product Q. So, this is the reaction we are looking at. Okay. Now, again as defined, A and B are the reactants, P and Q are the products, small a, small b are the corresponding stoichiometric coefficients of the reactants, and small p, small q are the corresponding stoichiometric coefficients of the products. Good. Now, what we will do is we will bring in one more term or parameter, that is something referred to as the degree of advancement of a reaction. Now, it is very similar to something which you have known from other topics in chemistry, which is the degree of dissociation. Here we say there is a degree of advancement. This degree of advancement is given by the symbol xi. Okay. The degree of advancement is given by the symbol xi. So, this tells you by how much the reaction has progressed or advanced as a function of time, right. Now, what we can do is we can write a certain expression which I say that n I will just tell you what these mean, is equal to n I naught or 0 plus nu I xi. Okay. So, if xi is the degree of advancement of the reaction, and let this be equation 1, if xi is the degree of advancement of the reaction, you know what I can write is the Ni, what is Ni? It is the number of moles of the chemical species I. So, that specific chemical species. So, I will write in detail later, but just to make the point or make the connection. So, if this I was referring to A, then this would be N A. So, it is then N A means the number of moles of A, or N I is the number of moles of the reactant or the product represented by that I, this A, B being the reactants or P, Q being the products. Now, what about Ni naught? So, this Ni naught is very significant. So, this Ni naught or 0 is the number of moles of the chemical species I when xi is equal to 0. So, it is the number of moles of chemical species I when the degree of advancement, as I said, the degree of advancement, I write it again, the degree of advancement of the reaction is 0. You go back to this equation. So, Ni is equal to Ni 0 plus nu I times xi. If xi is equal to 0, as I was telling you, if xi is equal to 0, then Ni is equal to Ni 0. So, what does this mean? This means that this is the initial concentration, the initial number of moles. Here I am referring to the number of moles, I have not yet brought in the volume, but which will convert it to the concentration units. So, the initial number of moles is at that point where the xi is 0, that means the reaction has not advanced at all. So, this is your initial condition. Okay. Again, what is nu I? By this time you know that nu I is the corresponding stoichiometric coefficient. Okay. So, now what we have done is we have taken this equation and we have tried to define each and every term in this equation, where Ni is the number of moles of the chemical species I, right. Then Ni naught, what is Ni naught or Ni 0? Ni 0 is that number of moles of the species when xi is equal to 0, that means the degree of advancement of the reaction is 0, that means the reaction has not progressed at all. And what about nu I? As you just figured out in our previous discussion, right, a few minutes ago, it is the corresponding stoichiometric coefficient, whether we are talking about a reactant or whether we are talking about a product, right. Now, as defined by kinetics, right, what is kinetics? Kinetics means you are looking at the change as a function of time, right, that is what kinetics is. So, what we will do now is we will go back to equation 1. So, let me write that again. We will go back to equation 1, which is Ni 0 plus nu I xi. So, this was our equation 1, right. Now, if this is our equation 1, because it is a change with respect to time, what we do is we differentiate this equation with respect to time. So, differentiate 1 with respect to time, because that is what kinetic is. We want to follow something as a function of time, that means how it changes with respect to time. So, then this equation becomes d Ni over d of t is equal to d Ni 0 over d of t plus d nu I xi over d of t. Now, pay attention. So, what have you done? You have done, what you have done is you have taken 1 and you have differentiated each and every term of that equation with respect to t. Okay. Let this be equation 2. So, some simplifications can be done straight away. Look at this term. This term is equal to 0. Why is it equal to 0? It is equal to 0 because differentiation of a constant with respect to time, in this case with respect to time, will obviously be 0, right, because it does not change, there is no change with respect to time. So, what is Ni naught? So, Ni naught, as based on our definition, is the initial number of moles, which is a constant, right. So, Ni naught is the number of moles where xi was 0. So, Ni naught essentially is the number of moles I started with. Okay. So, again I define, because Ni naught is a constant which as defined was the initial number of moles, hence d Ni over d of t is equal to 0. So, this is d Ni 0 of d of t is equal to 0. So, that means the initial concentration or the initial number of moles in this case of that particular reactant or product is known to you when xi is equal to 0. That means, when the reaction has not yet progressed at all, and because this is a constant, because you know it, then the differentiation of this with respect to time is 0. Okay. The next point is, if you look at this factor now, or this term over d of t, this can be written as nu I d xi d of t. Why can I write that? The reason I can write this is because nu I is a constant, right. What is nu I? This is a constant. Why is it a constant? This is my stoichiometric coefficient of that species I. So, then simplifying this, whatever we have done, we put this back in equation 2 and see what we get. So, then I have this d Ni over d of t is equal to nu I d xi over d of t, or I can write it like this, xi over d of t is equal to 1 by nu I d Ni over d of t. So, if I give this, say, equation number 3, this is a very important step. This is a very important step. You will realize that this term d xi over d of t, what does it say? It is the rate of advancement of the reaction, or we can simply say the rate of the reaction. We can simply say the rate of the reaction, right. So, you already have a term which gives you the rate of the reaction, and what is that? It is the way, or the differentiation of your degree of advancement with respect to time, that is d xi by dt, that is the rate of the reaction or the rate of advancement of the reaction or the rate of progress of the reaction, does not matter which way you define it. Now, that is equal to what? That is equal to 1 by nu I, where nu I is the stoichiometric coefficient, times d of n I over d of t. And what does this mean? It means that d of n I over d of t represents what? The change in the number of moles of species I over time. This times the inverse of the stoichiometric coefficient, which is 1 by nu I, is equal to the degree of advancement of the reaction. It is very similar. It is very similar to something you must have seen in any discussion on chemical kinetics, or something we are going to discuss down the line. But what you have to understand is one more thing. If you go back to this equation, when I am writing this, Ni is the number of moles, Ni0 is the number of moles at the initial time when xi is equal to 0, nu y is a constant, it is a stoichiometric coefficient, hence this xi is also the number of moles by which the reaction has advanced. So, then d xi by dt, when we are doing this, when we are writing this equation finally, when we are writing this equation finally, equation 3, everything is in terms of the change in number of moles. Yes, number of moles is proportional to concentration, but I have not yet brought in the concentration as yet, that means the volume is not yet brought in. Whatever this reaction is representing is the advancement of the reaction in terms of the number of moles being expressed like this. So, that means d psi by dt, which is the change in the advancement of the reaction, is equal to 1 by nu I d n I over d of t. So, this is how the very familiar equation you have seen or you see typically being discussed in books on chemical kinetics, in any book on chemical kinetics comes about. Now, to elaborate this a little more, let us go back to our reaction. So, if you remember what a reaction was, I will write again because we are flipping through pages. So, we might forget B giving P and Q. So, this was the one we started with. Then based on equation 1, we had said that N I is equal to N I 0 plus nu I xi, right. This was equation 1. Now, if you remember equation, this was our equation 1. Now, suppose I am doing it for I, where I is A, that means I am taking the reactant A. If I am taking the reactant A, how does this equation change, or how do we make this equation more visible to you? So, then because I is A, I can write N of A is equal to N of A 0 or not. So, this N of A 0 means what? Means the initial number of moles of A you had at time 0, where the reaction had not yet started, that means the degree of advancement of the reaction was 0, plus nu of A and then xi. Let me go ahead and write this one like this. So, N of A is equal to N of A not. Now, remember, going back to our discussion today in the initial part of the class, nu of A, this is the stoichiometric coefficient of the reactant A, and I told you that the stoichiometric coefficient of the reactant A is going to have a negative sign. So, then I give minus A. So, this being A with the negative sign, the reactant times xi. So, then if I differentiate it, then I differentiate it dt. So, this is equal to what? N A over d of t minus dt, right, or I can write it plus right now, then minus A xi. And going forward, it should be very clear to you that this is equal to 0, and hence this equation can now be written as d of N A over d of t is equal to, the first term was 0, then minus A d xi over d of t, or as we had written again before 1 by A d n A over d of t. So, now what have you done? What you have done is, or what we have done is, that we have expressed this rate of reaction, we have expressed this rate of reaction in terms of the change in the number of moles of A, which is reactant A. So, to carry on with this, suppose I try to express this in terms of the reactant B. See where I say, now let I be B, the reactant B, then obviously I have N B, which is the number of moles of B, is equal to N B naught, that is the initial number of moles of B I had present, plus nu B, the stoichiometric coefficient associated with the reactant B, then the corresponding xi. Again nu B is negative, that means N B is N B naught minus B xi. I differentiate with respect to time, d n B over d of t is equal to d n B naught over d of t plus and once I have done this, realize that this one is again 0 and I have d n B over d of t is equal to minus B d xi over d of t, or I can write d xi over d of t is equal to minus 1 by B d n B over d of t. So, which is very similar to what we had done here. I did not write the rest. So, from here I can write d of n A d of t is equal to minus A d xi over d of t, right. If you look at these two, here you can see what I have done. Here d xi by dt is equal to minus 1 by B d n B over d of t, right. Here also you can write d xi by dt is equal to minus 1 by A d n A over d of t. So, let me write here. So, let me write this one here, then I can write likewise that d xi over d of t is equal to minus 1 by A d n A over d of t. What is the similarity? Similarity is this, or are these, there are similarities. In both cases you have the rate of the reaction d xi by dt. The rate of the reaction is being expressed either in terms of the reactant A, the reactant B, right, which is d n A over d of t or d n B over d of t. That means, the change in the number of moles of reactant A or reactant B is a function of time. What are these associated with on the right hand side? These are associated with the corresponding, the inverse of the corresponding stoichiometric coefficients. So, for A it is 1 by A, for B it is 1 by B. Not only that, go back to our discussion in the previous class or with the initial part of this class, where we were saying that the rate of the reaction in terms of reactants are always associated with a negative quantity, isn't it? And you see this negative is coming out. Where does this negative come out? In this case, where we have said negative, this negative is coming out from the fact that your stoichiometric coefficient of the reactant by definition is negative, and hence you get that corresponding rates of reactions both in terms of the reactant A or in terms of reactant B. So, obviously, it goes without saying that if I now go to the product side, a similar thing would come about. So, let us now again say for the same reaction, let me write the reaction again, giving P plus Q with the corresponding stoichiometric coefficients. Let I be now P. Okay. So, that means now I represents the product P. If I represent the product P, then I can write N P is equal to N P 0 plus nu I or nu P, I would write nu P then xi. Okay. We go ahead and simplify it a little further. So, N P is equal to N P naught. Now, we say plus P then psi. So, this is where you note the difference between that of a reactant and that of a product. So, in case of the reactant, the stoichiometric coefficient had a negative quantity, was a negative quantity, had a negative sign. But in case of the product, because we are getting the product, we are producing the product, right, as the reaction goes by, the product is coming into existence, its concentration is increasing. So, the stoichiometric coefficient of the product typically is given a positive value, right, it is associated with a positive sign. Hence, you can differentiate it again, P by d of t is equal to d n p 0 over d of t plus d of t then p xi. Again this is equal to 0, right, because N p not being the initial number of moles of P, the product P is a constant, you know that. So, we can write d n p over d of t is equal to P d xi over d of t. Therefore, I can write d xi over d of t is equal to 1 by P d n p over d of t, right. So, see what we have. So, this is what we had for the reactant B, this is what we had for the reactant A. So, that means d xi by dt, the rate of the reaction was given by minus 1 by a dNA over d of t. Okay. In terms of B, the reactant B, d xi by dt was given by minus 1 by b dNB over d of t. In terms of the product, however, d xi over d of t is given by 1 by p, no negative sign, a positive sign, dNP over d of t, right. Hence, extending this, so it is left as an exercise for you to show that d xi by dt is equal to 1 by q dNq over d of t. I can write this straight away, that d xi over d of t can be expressed how? Minus 1 by a dNA over d of t. This is equal to minus 1 by b dNB over d of t. This is equal to 1 by p dNP over d of t, and this is equal to 1 by q dNq over d of t. So, what we have been able to do through this exercise is we have been able to define the rate of the reaction, which is d xi by dt. That means, the rate of advancement of the reaction, that is what your reaction kinetics is, or defined as, is defined in terms of what here, in terms of the rate of disappearance of the products A and B, and also the rate of appearance of the products P and Q, these being associated with the corresponding stoichiometric coefficients, and the stoichiometric coefficients are also associated with the respective signs. What are those? For the reactant species, the stoichiometric coefficients come with negative signs. For the product species, the stoichiometric coefficients come with positive signs, right. This is extremely important for you to keep in mind. Never forget this, that the stoichiometric coefficient, I repeat, the stoichiometric coefficient associated with the reactant is a negative number, that means it is associated with negative sign, while the stoichiometric coefficient for the product species is associated with the positive sign. Again, just to clarify what I said just now, the stoichiometric coefficient, the stoichiometric coefficient is always positive, okay, is always positive. Only when it is for the reactant, we precede it, that means we put a negative sign before the stoichiometric coefficient. If it is product, we put a positive sign before the stoichiometric coefficient, and this obviously is understandable based on a discussion. Why? Because the reactant we are losing as a function of time, so we put a negative sign before the stoichiometric coefficient to represent the fact that it is decreasing as a function of time, and the product we put a positive sign to say or to represent that this species or product is coming into existence rather, that means growing as a function of time. Hence, again as a clarification, please remember the stoichiometric coefficient is always positive though. It is just that when we define a reactant or a product, if it is a reactant then we precede it by a negative sign, if it is a product then there is a positive sign before the stoichiometric reactant, rather the stoichiometric coefficient, okay, because we want to differentiate between the reactant and the product, and we know that in any reaction the reactant is going to be lost and the product is going to be produced or come into existence. Okay. What we can do is we can just quickly take reaction, a specific reaction or chemical reaction or equation, and see how this comes out. So, let us consider this 2N2O5. Okay. I am considering what? I am considering the decomposition of N2O5 2 plus O2. Based on this reaction, N2O5 is my reactant species. I am looking at the decomposition of that. Decomposition into what? There are two products, 4NO2, NO2 plus O2. So, the products are NO2 and O2, and then obviously you have to make sure that the reaction is balanced. Then what can I do? I go back and I look at this definition of d psi by dt. Based on this definition, can I write down the degree of advancement of the reaction for this specific equation? Okay. How do I write it? So, I write then d psi by d of t is equal to, let us consider the reactant first. The reactant is d number of moles of N2O5 over d of t. It should be associated with its corresponding stoichiometric coefficient, but with a negative sign. What is that? I write it is minus 1 by 2. Why? Because this 2 is the corresponding stoichiometric coefficient of N2O5, and new N2O5 has to have or has to be associated with a negative quantity. So, that is what I have out here. So, this is the only reactant species we have. Then this is equal to, I write the degree of advancement of the reaction or d psi by dt in terms of the products. This would be d, the change in number of moles of NO2 with respect to time, and I will be having 1 by 4 out here. Similarly, I can write d, sorry, let me change this again, let me write it here clearly, d n 2 over d of t. What should I write here? You see, for NO2 the stoichiometric coefficient was 4, for O2 the stoichiometric coefficient is 1. So, it is 1 by 1. So, I am not writing anything out here because it is essentially 1 times d NO2 over d of t. So, going back to this expression again of for d psi of d of t, we have taken a specific reaction, we are expressing d psi over d of t, that means the rate of the reaction in terms of these given species. So, for N2O5 which is the reactant, it is minus 1 by 2, 2 being the corresponding stoichiometric coefficient, into the rate of change of number of moles of N2O5, right, or d N2O5 of d of t is obviously as a function of time. This is equal to 1 by 4. Remember, this is a positive, this is a product NO2, it is a positive quantity or positive sign. So, 1 by 4 dNO2 over d of t. If that is the case, you can see that we have, this is a positive sign out here. So, it is 1 by 4 dNO2 over d of t, right, and this is equal to the change in the number of moles of oxygen over time. What is the stoichiometric coefficient? It is 1 or plus 1, and hence this is how it comes about. So, hopefully you understand that this is how the rates of reactions are written in terms of the change in the number of moles. Now, generally what happens is all these things are done under constant volume conditions, right. All these things are done under constant volume conditions. So, let us take a specific example, or let us go back to our equation 1. So, you will understand what I am trying to say. So, we can say, since most of the reactions are done under constant volume conditions, then from 1, which was Ni naught plus nu I xi, this was our equation 1, right, and we had written d xi over d of t is equal to 1 by nu I d Ni over d of t. Think this was equation 3. Because this is done at constant volume, what I can write is, by definition this is constant volume, what I can do is I can write like this, 1 by V. So, I put 1 by V on the left hand side of the equation, d xi over d of t is equal to 1 by V. Because I put in 1 by V on this side, I have to make sure that I cancel by the same factor on the other side, then 1 by nu I d Ni over d of t. Again, keep in mind that V, which is the volume, is constant. V is constant. Now, if this is constant, remember this equation. What I can do out here is I can take this, I can bring V inside this differential form, say I can V inside this derivative, right, and hence I can write d, then in within brackets xi V d of t. See, I have brought in 1 by V inside, or I have gotten 1 by V inside, is equal to 1 by nu I, then d Ni V d of t. By doing this simple assumption, which is mostly valid for most of the reactions, that is what you are doing reactions at constant volume. What about Ni by V? So, see, this is the rate of the reaction. So, again I write d xi by V d of t is equal to 1 by nu I, the stoichiometric coefficient obviously remains as it is a constant, right. Then this can be written as the concentration of the species I over d of t. So, this I is concentration of species I. Now, immediately you realize that you have come back, or you have been able to reach a point which is very familiar to you and is used universally in chemical kinetics. What is it? That the rate of the reaction which is this, is given by the change in concentration of that chemical species, in this case which is I, over d of t, associated with 1 by nu I, when nu I is the corresponding stoichiometric coefficient. And how did we make this conversion from Ni over V to concentration of I? It is very simple. Simple is that what is concentration? Suppose molar concentration is moles over liter. What is Ni? Ni is the number of moles, and if you have V in liters, you can always do the conversion. So, you have the corresponding concentration term. So, this again is an extremely important equation. I have to see what is the number I can give. Just let me check. Let me give this equation 4, and remember now this is the rate of reaction. So, the rate of the reaction is having this expression, which is given by the change in concentration of the species I with respect to time, weighted by or is associated by the inverse of its or the corresponding stoichiometric coefficient of species I, right. Good. So, now what we have done is we have been able to define the rate of the reaction in terms of the change in constant of the reaction or the change in constant of the reactant species or the product species, right, whatever you can think of using, you can feel free to use as a function of time. So, what I will do is I will start with a specific example. Let us do an example and see whether we have some whether we have a feeling of what we have just discussed right now. So, what we are going to do is we take an example that we are going to focus on. So, here we have acetaldehyde gaseous giving me methane plus carbon monoxide both in the gaseous states. Now, what is the question or what is the problem? The problem is that the rate of this reaction can be followed by measuring the pressure in the system at constant volume and temperature. Again, you are given this reaction acetaldehyde going to methane and carbon monoxide, and it said that the rate of this reaction can be followed by measuring the pressure in the system at constant volume and temperature. So, that means the volume of the vessel and the temperature are being kept constant. So, how do we proceed with this based on the discussions we had earlier? So, let me write down the equation again. So, before writing down, let me tell you this, that when we are going to go through this problem, one assumption we are going to take is the following: assume ideal gas behavior, of the gases. Assume ideal gas behavior of the gases. So, let me write down the reaction again for the sake of convenience, because this is where we will start working with the problem. So, now having written the reaction down, let us think about the initial phase or the starting of the reaction. So, at the initial phase, so if I write this one as initial, so if I write this one as my initial condition, so the initially I have n naught moles of acetaldehyde in the reaction vessel, but there are no moles of any of the products present. So, that means the only species I have at the start of the reaction is acetaldehyde, and of that I have N naught or N0 number of moles. Now, with progress of the reaction, what will happen is, so here we write with reaction progress. So, with reaction progress I can write N naught CH3 CHO minus xi, xi being the extent of reaction or the degree of advancement of the reaction, which we just saw, then xi and xi. So, that means the way the reaction is advancing, what we are having? We are having, as the reaction is progressing, N naught moles of acetaldehyde minus xi moles, which is the degree by which the reaction is advanced. Along with this, I have xi moles of CH4, a gas formed, and xi moles of carbon monoxide formed. Okay. So, once we have this, once we have this, let us now write down the number of moles of the individual components. So, that means NCH3 CHO is equal to N naught CH3 CHO plus nu I psi. But remember, this being a reactant, you are losing acetaldehyde as the reaction is progressing. So, nu I out here is negative. The value of nu I you saw from the previous slide or equation is 1, that is the coefficient is 1. Hence, what we do now out here is we rewrite it as follows, where NCH3 CHO is equal to N naught CH3 CHO minus xi, right. So, nu I, the value of nu I is 1, and because you are losing acetaldehyde as a function of time, hence its sign is negative. So, this one is important for the setup of the problem or the way we are going to work with the problem. Then accordingly, I can write for methane. So, the number of moles of methane, which is NCH4, like we wrote the number of moles of acetaldehyde NCH2CHO, the number of moles of methane can be given by N naught CH4 plus nu I xi. Okay. Again, if you go back to the reaction, the coefficient before CH4 is 1, right. Same for carbon monoxide, the coefficient before carbon monoxide is 1. Hence, for methane, then this nu I has a value of 1 and the sign is positive because reaction is progressing and the product is forming. So, I can write then N CH4 is equal to N naught CH4 plus xi. Now, also N naught CH4, which is the initial number of moles of CH4, if you remember from the previous discussion, is 0. The same thing is also for carbon monoxide. So, I can further simplify this by writing that N CH4 is equal to what? Xi. Why? Because N naught CH4 is equal to 0. So, this is again another important piece of information that you will need while we walk through the problem. So, we are left with one more component, which is one of the products, carbon monoxide, very similar to that of methane. So, how do we write that? So, then for carbon monoxide, so what I write, NCO, that is the number of moles of carbon monoxide, is equal to N naught CO, that is the initial number of moles of carbon monoxide present, plus nu I xi. Same thing as that of methane, this is equal to 0, right, N naught carbon monoxide is equal to 0, and nu I is plus 1. Hence, I write N CO is equal to 0 plus xi, or N CO is equal to xi. So, then in a nutshell, what have we done? We have been able to express the number of moles of the respective components of the reaction, be it reactant, which is acetaldehyde, or be they products, which are methane and carbon monoxide, in terms of the extent of the reaction, which is xi. So, we will start from this in the next class.